everyone. Welcome to the afternoon session. Our first speaker this afternoon is Alex Kontorovich, and we'll be speaking on rough structure and classification revisited.
Hey, thank you so much. Thanks to the organizers for the invitation and the opportunity to speak here. It's always a great pleasure to be back in the room where that picture was taken. It's been a few years since I've been at the Newton Institute, and it's always a lot of fun. For those of you that don't recognize the title, one of you does already. So a few weeks ago, I was having a conversation with Sarnak about various thoughts. This was at the Institute, about AI, the future of mathematics, where things are going. And he says, Gowers said all of this years and years ago. Go read Gowers. So I went and I read a paper called Rough Structure and Classification. This was following a conference in Tel Aviv in the year 2000, a quarter century ago. And so let's look at what's in here. Now, the actual rough structure and classification he doesn't get to until section 3. And these ideas were incredibly prescient. What's that?
Oh, I was just asking, is this the visions of mathematics?
Yes. Yeah, exactly. In GAFA, yeah. So I'm not going to talk about any of this stuff, but just to point out the direction that these ideas went in the decade after this article. Okay, there were some antecedents in work of Freiman and Ruschen, but basically this, ideas of approximate groups, approximate rings, like the sum product theorem is if you have a subset of a ring and the sum set doesn't grow and the product set doesn't grow, like if you're not getting more elements by adding or multiplying things, then you must already almost be itself, the entire ring itself. So these ideas were extremely influential. All kinds of fantastic things happened. So, not that you need more evidence that Tim can see far into the future, but it's section 2 of this paper that I want to focus on today, which has the following title: Will Mathematics Exist in 2099? So we're a quarter of the way there, from 2000 to 2025, and let's see. So I wanted to decompose these ideas into 4 categories: discovery, how do we come up with new theorems, what's the process by which we arrive at proofs, by truths. Separately, how do we understand those things? How do we communicate them to others? And I realized that there's basically, I had no way of distinguishing between understanding for myself and communicating to others, so that became one category. And of course, another category is teaching. The difference between communicating and teaching is communicating with professional mathematicians as opposed to teaching to beginners. People who are new to the subject. So let's jump right in. So in discovery, if you go a little bit into Tim's chapter 2, he says, let me return to the question of automating mathematics and present an imagined dialogue between a mathematician and computer in 2 or 3 decades. Here we are. Okay. The idea of the dialogue is that the computer is helpful to the mathematician while not doing anything particularly clever. This represents an unthreatening intermediate stage between what we have now in the year 2000, where computers act as slaves doing unbelievably boring calculations, and full automation of mathematics. I've written the dialogue in English, but it's supposed to be a translation of a more formal language, which has not yet been invented. Let's talk about not doing anything particularly clever before we get to the actual dialogue. So, of course, I'm referring to LLMs. Lots of people mean different things, so I'm sorry to insult your intelligence by defining what I mean by an LLM, but let's just, for 1 second, say what that is. I was standing at platform 9 3/4 this morning, so I had to throw in this page. So you're reading to the bottom of a page, and I'm talking about a physical book. I don't know if some youngsters here know what that is. You actually have to turn the page with your fingers, and you often fumble to turn the page. And as you read the bottom of a page, your brain can't help but imagine what the next word is. So there were Horcruxes out there somewhere. He didn't know the faintest idea where they could be. He didn't even know what all of them were. Meanwhile, he was at a loss to know how to what. Okay, so this is, maybe some of you would say how to destroy the Horcruxes, or how to find the Horcruxes, or how to sandwich, or I don't know, right? So there's all kinds of next words, and maybe 20% of you would say destroy, and 7% would say find, and almost none of you would say sandwich. So I think of this as, you guys, is this a show that appears in the UK, Family Feud? Yeah. So its survey says it's not what the answer is. There's a distribution of possible answers, each one with a certain score. That's, to me, what I mean by a language model. It's a function whose input is context, the sequence of tokens, and the output is a probability distribution of next token. I want to separate that from a chatbot. A chatbot sits on top of an LLM and decides, given your choice of temperature, given your choice of how you're going to select from this distribution what the next token is. Once you add that token to the context, you just run it again and again and again until one of the tokens says, stop talking. Okay? So let's separate the model of language, which gives you a distribution given the context, and the chatbot, which is actually producing that conversation. And I want to point out that this chatbot is extremely stochastic. It's random. It's not just random. It's random on top of random on top of random, because every time you make a choice, it's a Brownian motion, right? You're changing the course of the conversation every time you sample from the distribution. Okay, so we all know what an LLM is, so let's go into what the actual conversation was. So here was the conversation. It's a little hard to read. Let's zoom in on it, but just, this is 25 years ago what we today experience when we talk to an LLM. So prescient ideas. This is one of the earliest instances of prompt engineering. So the mathematician says, is the following true? We're looking for 3-term progressions in a set of positive density. The computer says yes. If A is not empty, set D equals 0. Yeah, okay, fine, all right. What if D is not allowed to be 0? So this already is pointing to the fact that it's hard to state problems exactly, correctly, formally, and keep the meaning if you're working in a formal system. So just to illustrate this, I ran an exercise a week ago. So DeepMind put out this formal conjectures. I thought it was a fun thing to experiment with LLMs. So I asked Claude, state for me the Bateman-Horn conjecture. It doesn't matter if you know what the Bateman-Horn conjecture is. It's something in number theory. It says the statement. The statement is, it knows the conjecture. It's read it on Wikipedia. You have a bunch of distinctly reducible polynomials. Then the proportion, the amount of the count of the number of n up to x, for which they're all prime, if they're irreducible and satisfy some local obstructions, is some constant, which is a product of local factors, times this x over log to the kx. Great, it knew the Bateman-Horn conjecture. So then I said, great, can you please formalize a statement in Lean 4 using as much MATLib built-in API? And it just did it. It spat out in one shot nearly perfect formalization of the Bateman-Horn conjecture. Now it's a conjecture, so of course it's not giving me the proof, but it's made the statement and just translated the statement that the first prompt put the vector in the direction of the model where it knows Bateman-Horn, and the second prompt asked it for Lean, and it just gave it to me. Okay, but it wasn't quite perfect, because in particular, if you remember, the first thing we said is that the polynomials had to be distinct. And so here it's trying to say the polynomials are distinct. For all f and g in the set of polynomials, well, you can't just say f is not equal to g, because f and f, it won't hold for f and f. It's trying to say distinct, but it doesn't know how, because finset already, if you have a finset, it's already not a multiset. There is no distinct. You just need to cross that line out. But it tried to say something, okay, that's not such a bad thing because it said something that's vacuous. But it was worse than that, because I sent this to a few friends, and Will Salmon writes to me and says, hey guys, you missed D. If you actually look at Wikipedia, what we should have had, oh, come on. There we are. There was this constant that I was very happy to see, but there was supposed to be a denominator, which is the product of the degrees of the polynomials. We're off by a constant from the correct mean term. And, well, it wasn't there. It wasn't there in its formulation, and I didn't think to see it. And Will says, either you or Claude missed it. Let me correct Will. I missed it. I'm responsible. If I'm the mathematician, and I go and I use these tools, however I use them, my feeling about this is that I can't say, oh, it was Claude that did it. No, I made the choice to use Claude. I'm the one who's responsible for any of the outcomes. In the same way that if I'm in a self-driving car and I choose to turn on the self-driving feature and I'm supposed to be, holding the steering wheel or something, the car crashes, my insurance is going to pay. Okay, that's a small aside. We're still not quite there because there's one more condition that was kind of skipped over by everyone up to this point, which is that the statement as stated is not true if the polynomial is the constant polynomial. Now, okay, so trivially, if that constant is not a prime, then there's 0, and if it is a prime, then it just reduces to the previous statement, the other version with the other polynomials, but it's wrong as stated. The problem was still wrong as stated until we included the, so we had to add that the degree was strictly positive. Okay, so the point here is that mathematically speaking, these are completely, okay, there's a constant, and this, you know, they're typos, they're trivialities, but if you're working in a formal system and you're trying to find a formal proof, you have to get this exactly right, or else you're doing the wrong thing. So getting the meaning right is difficult. That was one example. Let me show you another example. This is from a beautiful paper of David Loeffler and Michael Stoll, talking about the formalization of the zeta functions and L functions in Lean. So a lot of people say the Riemann zeta function is summation 1 over n to the s. That's absolutely wrong. That's like the Euler zeta function or the Bernoulli zeta function. The reason it's called the Riemann zeta function is because he figured out what you're supposed to do is take a theta function, take its Mellin transform, and divide by a gamma. Okay, that's the real zeta function. And here's the Riemann hypothesis. If this expression evaluates to 0, okay, there's some trivial zeros when the real part of s is negative, so let's say the real part of s is positive. That only happens if the real part of s is a half. Now, those of you that are familiar with Lean know that there are some issues with division that don't work exactly the same way as they do in human mathematics. And moreover, in Lean, the zeta function is defined on the type of complex numbers. That's its domain. So it's going to have some value at s equals 1, and there could be a problem. So they point this out. In fact, I think it was Kevin and Jordan Ellenberg who pointed this out, that the Riemann hypothesis, as stated formally, may have been wrong if the junk value that resulted from the formalization of zeta at 1 just happened to be 0. Okay? So this is the kind of thing that an AI can come along and give you a million-line proof and say, okay, I solved the Riemann hypothesis in the negative, and there's a 0 off the line, and you know, okay, so where is it? It's at 1. Because you got the definition not wrong. It's a junk value. It doesn't matter what that value is. But there is some value that comes out of the proof. And it turns out that it's not 0, so they're okay. But so these are just two little vignettes about the difficulty when you're working in formal systems of making sure that you have statements exactly correct, or else you don't know what you're doing. So then I was having this conversation with Christian Szegedy, and he said, not quite like this, but he said, don't you believe in mathematics? What do you mean? He said, you're a mathematician. You do this for a living. Don't you believe that your subject is beautiful? Don't you believe it's robust? Doesn't matter if you get a definition wrong. Are you nuts? What do you mean it doesn't matter if I get a definition wrong? Then I'm not talking about the right thing. He says, right. And if you're not talking about the right thing, you won't be able to prove the theorems that you want to prove. Maybe locally you'll get the statement wrong. Maybe locally you'll get the definition wrong. And as you develop more and more mathematics as a result of those definitions and as a result of those theorems, you'll know that something hasn't gone right, and you'll have to refactor. You'll feel, mathematics is robust, and you'll feel wrong definitions in the process of creating more and more theorems. This is completely shocking to me. But it's indeed something that has happened time and again. In MATLib itself, the notion of a group had to be refactored multiple times because...
we do it in formal mathematics. I mean, this is the exact same argument that people are always giving for informal mathematics.
Yeah, that if the definition is wrong, it'll have to get fixed later. So he says, don't worry about the formal statement being wrong, even the formal definition being wrong.
Schultz's definition of a perfectoid space is different to his second definition.
Yeah. Yeah, so the point is, as long as, if you want to do, I mean, Christian's dream is that we should all just be working on auto-formalization, and nobody should be doing human formalization, right? And I said, that's crazy because, you know, first of all, we should be responsible for what comes out of it, and we have to own the statements. And he said, don't worry about the statements. If it gets it wrong, it'll know, and you need a refactor tool. But if mathematics is truly robust, and you believe that to be the case, then it's not such a big deal. I was shocked by this. Okay. Anyway, so important results will eventually be right in the long term if you believe that mathematics isn't just something we make up willy-nilly. Or the result isn't important. You got it wrong and it doesn't actually do anything, so it's not such a big deal that it's wrong. And we have lots of things in the literature that are wrong right now, today, and nobody's discovered it yet because no one's tried to use it for anything. Okay. So already in the very first line, there's, we're going to keep going like this, where every line of Tim's paper has all kinds of beautiful insights. So he starts right away with, can you find a plus d, and a plus 2d, and the computer says yes, that d equals 0. Okay, fine, that's not what I meant. Okay, it's hard to get the statement. So the conversation continues. Have you tried induction on n? You're telling Tim Gowers to try induction on n. Yeah, that's not a useful idea. So this is what many people refer to as a system 1 response. So let me explain what I mean by that. System 1, so this is the nomenclature from Danny Kahneman, popularized this way of discussing human brains, that we have two different ways that our brains work, System 1 and System 2. System 1 is effortless, immediate. If I ask you 3 plus 8, no one is sitting there, okay, 9, 10. You're not doing something careful, you just know the answer right away. Unlike if I ask you 437 times 82, maybe someone here can do it in their head. The rest of us have to take out a piece of paper and start carefully go through the calculation. So when a computer, whatever computer is doing, or when I do it by hand, I am following a long string of deterministic operations, each one of which has to be exactly right, or else the final answer is wrong. And so if you have something that takes 1,000 steps, and you're doing it with a stochastic process that has even a 99% certainty of getting each one of those steps right, what's the probability that all of them manage not to make a mistake, right? Everybody can do this calculation. System 1 processes cannot do things that take lots and lots of steps that need to be collated together. That said, even though they can't do deterministic things, System 1 responses can still be useful. And I learned this lesson during the pandemic, actually. I was thinking, what do we need a department for? Well, at tea time, that's the time where you can grab a colleague, take them to the blackboard and say, can I just ask you some really stupid question? And sometimes just the fact that you're asking the question to someone who's not in your field, which means you have to bring it down to a really basic level to explain it to them in 3 minutes. Sometimes I don't know if you have this experience. Sometimes I then understand what I need to do, but since I've asked the colleague the question, I have to politely stand there while they talk for 5 minutes, and then I say, thank you so much. I go back to my office and I realize, that's what I should be doing. So I have that experience too. Sometimes you type it into an LLM, you start saying, this is the problem I'm having, and then before you hit enter, you know what the answer is. Okay, but when your colleague responds, this is the point I want to make. When your colleague responds, they're always responding with System 1, right? Someone asks me a question at T. I'm shooting from the hip. I'm not sitting there doing a calculation. Oh, I think you should Cauchy-Schwarz and open the square and see what happens, right? So, but you go to T every day, and you ask enough of those stupid questions, and over time, you will get a lot of benefit from those kinds of System 1 responses. They could excite some, point your LLM vector in your brain into some interesting direction. When the pandemic started, I thought, that's okay, we don't have Department T anymore, but it doesn't matter, I can call up any friend, I'm not such a shy person, I'll email them and say, please let's hop on a quick Zoom call and I'll ask you a question. And that did not happen. Okay, so we need departments. We need that randomness lubricated by the cookies and tea. Relatedly, I'm probably among the youngest people who still had the experience. I don't do this anymore, but I at some point went to a library and opened up a journal looking for an article, and two pages before was some other completely unrelated thing that had a brilliant idea in there that was exactly the thing that I needed, that I never would have searched for. So I don't know how to ask an LLM, throw me a random paper out of nowhere. Just do it. Google has this I'm feeling lucky button. Claude should have a just tell me something. I don't know. Okay. So even though System 1 responses can be useful, I am baffled when I hear people trying to train LLMs to multiply 100-digit numbers. What are you doing? An LLM is a next token predictor. Why would that multiply numbers? It does. It can be trained up to a certain amount, and the bigger they get, the farther they go, but this is, to me, a waste of time. Use tools. You know what to do. In fact, the way that I computed 0.99 to the 1,000 is I asked Claude to do it for me, and Claude said, yeah, no problem. It wrote a Python script. It ran the Python script. It gave me the exact answer. You don't need to guess, right? Just use a tool. So this is why I wanted to separate chatbots from LLM. The chatbot can use the LLM, realize that it's supposed to use a tool, go and use that tool, accurately get an answer, and report that answer back to you. A little caveat, So the DeepMind folks were at the Institute a few weeks ago, and they were showing us an example where Gemini knew it was trying to compute the genus of some curve. It knew how to write the correct Sage code. It called Sage, and the genus was 2, and it said the answer was 1. Like, what is going on? How is this possible? So the reason it happened is that the call Sage tool was turned off. It wasn't actually allowed to call Sage, but it knew it was supposed to call Sage and give a response. So it did. It just answered, Sage says 1, even though it never ran Sage. Okay? So my takeaway from this is I never ask it to analyze data. I'll send it data. It'll analyze it, and I'll say, I don't trust you. Give me a Mathematica code or give me Python code that I can run myself away from you, where I can be sure that it's actually being run, and then I can analyze it. Trust but verify. Trust but verify. Okay. Where I'm getting to is if you're gonna try to reason and you want to use a tool, what tool should you use? Obviously, lean. Now again, lean means lots of different things in different contexts. So let me define terms what I mean by that. I sort of see in my mind's eye 4 places that people talk about lean. Lean itself is software for code verification. We have nothing to do with it, right? We're a sideshow. The fact that it can prove theorems is like a nice side thing, but it was originally intended for software verification. Of course, we're very happy that, and they're very happy that it found this application. MathLib is this massive, beautifully synthesized, interconnected library, making it possible to do these other things. Let's zero in on that a little bit. I have friends who write to me and say, you talk about this lean being so great. I opened up a MathLib page on number theory. I didn't understand a word. What is this nonsense? Why all these symbols? What the hell's going on? It's not for you to learn how to do math. It's not for you to learn how to do lean. It's an engineering project. It is not an educational project. That's my interpretation of MathLib. MathLib, to me, has a single-minded goal of getting to 1 million to 10 million to 100 million lines of code where everything works. Everything can talk to every library. It's not a place where you're supposed to go and learn how to formalize or what the mathematics is. There should be things on top of it that explain those things. I meant to say that when we were talking about groups, I was talking to Akshay Venkatesh, and he said, I don't know what a group is. So obviously he knows what a group is, but what's the actual definition? He said, it doesn't matter. It doesn't matter what the definition is. I don't know how to define it, but obviously I know what it is. I can use it. I know what theorems are true, what things aren't. I can give you a definition. I don't know if it's a good one. I don't care. It doesn't matter. In the same way, we should not, the rest of us, some people work very, very hard in MathLib to make sure that the rest of us don't have to know what the definition of a group is. We can just use it. There's API for it. There's theorems. There's tactics, and so on. So people work extremely hard to make good API so that the rest of us don't need to know it. By the way, speaking to Mario's talk, I think my guess is something like 90% of mathematicians took a foundational course in set theory, and maybe more or less?
Much less.
Less. In set theory. That's not just a course that everyone... Okay. Okay. I thought less. Fine. How much? 80?
15?
I don't know.
15?
In France, it would be maybe 1%.
There's one person who took set theory. Okay, but how many took dependent type theory? 0. Okay. So my point still stands. I don't know. My freshman year, I took set theory with John Conway. I assumed everyone had set theory. But I remember, set theory teaches you, you have to, there's Russell's paradox, you don't know what a set is, you have to define everything, like functions are sets and relations are sets, and everything's a set, right? And the very next semester, I'm taking algebraic topology, and so the professor, day 1, consider the space of continuous maps between these two topological spaces. Like an idiot, I raise my hand, excuse me, professor, how do we construct this out of Zermelo-Frankel? Right, it's like, get out, kid, I'm trying to get somewhere. So I realize it's a lie. We say we have to have foundations, we have to have this rigor, and we teach that foundation, and then we actually have to get somewhere and forget it, right? Let's go. Let's prove a theorem.
The first step in France, just don't do the foundation.
Just don't do the foundation. Well, it's nice to know. Well, I think it'll switch. I think in 10 years, whatever fraction of us would have taken set theory, instead we'll take dependent type theory, and the number will go in France from 1 down to 0. Okay. because it is the way that things work in practice. Okay, I'm going to come back to teaching later. Let's talk about research. So because MathLib is such a beautiful, massive resource, you can run all kinds of experiments on it. You can do large-scale formalization projects. Lots of people have talked about these kinds of things. Let me skip a discussion of the prime number theorem project. These things are not necessarily going into MathLib. MathLib has to have perfect code. People have talked about this already. But of course, as a tool for an LLM, this is exactly what you want to be using. You want to be sitting on top of MathLib, doing something, doing experiments, trying to see what you can prove, trying to understand something. So in order for an LLM to be able to use something like MathLib or just lean with MathLib as a tool, I think the essential thing that it needs to be able to do is what I call quasi-autoformalization. So let me explain why that's not the same thing as autoformalization. So here's my kind of picture of what I have in mind. Idea, this is where I want to sit. The conversation that Tim is having with the computer is at the level of ideas. Okay? What if you tried Cauchy-Schwarz here? What about four-term progressions? Let's just don't worry about statements yet. Once that idea turns into a statement, and informal is really the wrong word. I just didn't have. It should be natural language formal statement. I want an actual statement, but stated in natural language. So you can imagine an LLM, a chatbot, can take that idea and turn it into an informal statement, as you saw with Bateman-Horn. If there is a corresponding proof, it could spell out the corresponding proof. It can propose a natural language proof sketch. And so this is where I want to point out quasi means that I don't need this to happen completely automatically. At every step, check in with me. Here's the idea we're saying. Then the LLM, the chatbot comes back and says, here's what I think the natural language statement is. I don't like that. Let's play with it a little bit. Okay, now I'm happy with it. What do you think the proof is? Now it tells me a sketch in natural language of the proof. Okay, I'm happy with the sketch. Now let's move to the other side. So the other side is then we're going to take the natural language statement, make it a formal statement in Lean, and take all of the natural language steps and use that as a scaffold for a whole bunch of halves. So this is the part that in Thomas' talk yesterday, Thomas was describing our interaction. It was not quasi-auto-formalization because I was writing out the halves, and then alpha proof was filling in the saris. But there's no reason, you don't need me. The AI, chatbots can take these steps and with some guess and check and with a little bit of oversight from a human being can do this scaffolding quasi-automatically. And then, of course, once you've written out these things, you want to make sure that they actually close the goal you had in mind. If that's the case, then that's the stage at which you've sufficiently decomposed and scaffolded the original idea that's turned into a natural language statement so that you can send it to an automated prover like alpha proof and start just knocking out the saris and have a finished product. Okay. What's that? Okay. Any questions at any time, please interrupt. So, let me mention something that I learned from Heather, which is that filling in saris like these, as a human being, there are hundreds of thousands of theorems. When an LLM finds adcom, that's a bad LLM. We should not know the names of theorems. We should only know the names of a very small number of tactics. You should know as a mathematician why something is true. And if you know why it's true, then there should be a general purpose tactic that gets rid of all things of that nature. So if an LLM finds adcom, it's wrong. It should find ring. Give me the general purpose thing that you'll only need to use, that will solve a whole slew of problems. Yes?
Then in this case, we're thinking that as a good mathematician, we should think of ring, but an LLM that has memory much larger than us, isn't it, on the other hand, on the contrary, something good to find outcome, because at least we know that it's not just repeating ring many times in a row?
Yeah, so I guess I'm mixing matter. So as a human, I would want to be doing this, and then as an AI, I almost don't care how it does it, as long as Mario's not sticking bugs into it. Yeah, you're right. You're right. If the LLM wants to memorize adcom, fine. But
You don't want to see that.
I don't want to. Exactly.
We sort of want to have it readable, right? Up to some degree.
It would be much more readable if it was taking big steps. the goal of having it decomposed into a sufficiently fine scaffold is so that almost single tactics can knock it out. What shocked me, I mean, this really blew me away, was that alpha proof was coming up with like 10 lines of serious lean to get to the answer. The probability, again, 99% to the however many steps it had to take to get that right is shocking that it's that accurate. Okay, other questions here. So so what's the upshot? Even though LLMs are systems in and of themselves, if you can leverage with tools, things like this, and of course just building on top of Lean and MATLAB, it can become as useful as System 2. And in my estimation, the greatest challenge in the short term is getting this part to work. Okay, so back to the conversation. So have you tried induction? Was just a System 1 throwaway. It knew it had to say something. It thought maybe it'll get away with saying, have you tried induction? No, that was no help at all. The conversation continues a little bit longer, and the mathematician says, okay, well, random methods often give the best answer for problems like this. Let's try to prove that square root is best possible. The computer pauses for 1/1000th of a second and says, actually, no, there's a construction invariant, and downloads the paper. So there's a fascinating comment a couple of paragraphs later where Tim says, notice that it's important that the computer has access to a mathematical database which is more sophisticated than anything we have at present. And 25 years later, that database is exactly what the LLMs are so good at. You just start talking at them, and it'll point in a direction where it'll find something like Barron. So in terms of looking up literature, again, you can't trust what it says. You have to say, give me the link, and then go yourself to open the link and make sure it's not a 404 error, and make sure that the paper actually exists. There's some lawyers, I'm told, who got in trouble by not doing that second step. Anyway, so we have that database. Let me skip to another section in the paper. Tim says one way of explaining a proof, and explaining applies just as well to discovering a proof, is to show that it can be generated using what one might think of as standard mathematical reflexes. Some general methods to approach problems, just problem-solving techniques. And so here are a couple of those. If you're trying to prove P, is P a special case of Q? It's often, actually, in formalization, it's easier to prove a more general, more abstract, more general statement than it is to prove an individual statement. In the interest of time, let me not give a concrete example of that, but I think everyone knows what I'm talking about. If so, maybe Q can be appropriately modified. If not, then is Q even true? Try to prove Q instead of proving P, or step 5, try something else. Or modify a known argument. Maybe find a known statement Q that resembles P. Maybe there's something nearby P that one can prove. Can something be modified? Does this smell like something? This is exactly what alpha proof has been doing in taking the statement that the agent can prove and the statement that it's trying to prove, and just having LLMs generate nearby statements until they get far enough out that one of them can actually be proved. And now they start working inwards and generating more and more statements that the agent can prove until it can solve that problem. So they read this paper too, right? They're following along with this protocol. The paper continues, spotting patterns in special cases. Have I managed to think of any interesting ideas? If not, think about one of those interesting ideas. If not, make a cup of coffee and think about it and wait a while, right? This is human prompt engineering, is go for a walk. Why? Why does, if your brain is stuck in some vector, why does going for a walk and getting some coffee, get it unstuck and start pointing it in some other direction? I don't know, but it seems to work. Engineering, however our brains were engineered, it seems to work. And what Tim has discovered here is the latest reasoning models have a token called keep thinking. And it doesn't do anything. It just puts the entire context back through the model a couple more times. And for whatever reason, in practice, that seems to produce better answers. Okay, so there's a precursor to that sitting in this paper as well. Okay, let's talk about teaching. So let me give you an analogy to chess. Imagine that this is how we taught chess. Okay, class, so the game goes like this. Knight f3, then knight f6 is answered, c4, then g6, knight c3, bishop to g7. Okay, everybody with me so far? Then, right? Like, what a move. He did knight a4. Can you believe that? Okay, so maybe some of you are chess aficionados and you know what this is. If you're like me, this is just, I have no idea what's going on. You have to show me this. This I can follow. Okay, knight f3, okay, knight f6, fine. Then c4 is played. Now you can actually make sense of it because I showed you the game board. All the information is in the algebraic notation, but you know, help me out. Let me see the game board. So in the same way, well, my claim is that that first example is how we currently teach math. Let's look at that. So let's prove that root 2 is irrational. Completely true. Everybody knows the proof of root 2 is irrational. If not, then it's equal to a fraction in lowest terms. You square both sides, cross multiply, you get p squared equals 2q squared. Then p must be even, and then you're almost done. At every stage in this argument, there is a mathematical game board. What are the assumptions? What's to be proved? And it's changing at every stage, and yet I'm never showing it to you. You're supposed to build in your own mind. This is effortless for everybody here because you've had so much practice. It's system 1 for you, but for a beginner, it's extremely difficult. This is a system 2 process for them to track, just like it would be for me to track that chess game. I need to take out a chessboard and do the moves and see them in order to know where things are. Let's look at the same exact proof, but now I'm going to show you the game board. Okay, so at the beginning, root 2 is not irrational. There's rat.cast, which is the casting of the quotients of integers into equivalent sequences of Cauchy sequences and rationals. Equivalence classes of Cauchy sequence, that's that. And then the range of that is the rational is sitting inside the real, so I can say root 2 is not in that set. That's where we are at this point in the game board. Okay, if not, at that point in the game board, we have a new hypothesis called H, which is that root 2 is in the image, and our goal is false. This is completely trivial to all of you, again. But to someone brand new to theorem proving, it helps them just as much as it helps me to see the chessboard. If not, then it's equal to a fraction in lowest terms. Okay, so there exists P and Q, P and Q co-prime, and root 2 is that. And when you square both sides, okay, so now we square both sides, and you cross multiply, you get to this point in the. You see, if you show the game board at every single step, it just really makes it so much smoother for the person who's trying to take their first steps in this direction. So you would never, if you're teaching on a blackboard, it would just take way too long. It's too cumbersome to write all of this out. To at every stage pause and change the game board, you wouldn't do that. And it's unnecessary. We all learned without it. In fact, when I was talking to some other friends about this, they said, maybe it's important that people struggle and learn how to do those game boards in their mind so that they're really, really proficient. Maybe that's the only way to become proficient at high-level mathematics. I don't know. Maybe they're right. Although, do you ever really have to play chess blind? Can't you just always have a game board there? Is it such an important skill to be able to play it blind? Maybe it is. I'm not a...
Against a simultaneous, against like 10 people.
Well, that's just being able to do it really fast, right? You just look at the board and you know what move you want to
If
make.
you're assessing counterfactuals, right? When you're doing an assessment, you look at alternate moves, then you see it ahead.
Yeah, absolutely, absolutely.
You can't have all the boards while you're playing.
Yep.
So you do that.
Yep, that's a really great point. So for the same reason, maybe at the beginning you do this and then you take it away, and then you let them develop the feeling of what, you know, getting that, being able to follow 3 moves of an argument down. Okay, so this is exactly what teaching with lean allows. What I have in mind is just writing code live, not worrying about perfect formalization, leaving some sorries there, but at least being able to track the game board. Just like in the quasi-auto formalization, scaffolding the argument and leaving the technical sorries, you can just leave them when you're teaching, if you have in mind to show the full argument. Okay, so let's get to teaching, and this is why I have teaching. It's not teaching comes out of MATLAB. Teaching comes out of both MATLAB and Lean. So you don't need to immediately jump to the perfect MATLAB code in the same way that we do still teach Riemannian integration, Riemann integrals, even though a few years later we're going to tell them, oh, by the way, that wasn't the right way to do things. Here's the Lebesgue integral. Okay, so there's nothing wrong with teaching epsilon and deltas and not jumping straight to filter.tends to. So using epsilons and deltas is less challenging than jumping straight to filters, but it also makes it easy to catch beginner mistakes. Supposedly Cauchy proved, when he was first trying to make things formal, epsilons and deltas don't appear until Weierstrass, like 1860s, but Cauchy was trying to do something like this, and apparently he proved that limits of continuous functions were continuous around the same time that Fourier proved that he could add up sines and cosines and get a sawtooth. Okay, so you break it, you bought it. They broke math, and they had to figure out what to do. And in a sense, you could trace this back to, we're in the Newton Institute, you can trace it back to Newton, and of course Leibniz, Bernoulli, and Euler, who wrote hundreds of papers, thousands of papers, without having the axiomatic foundations, and there were no problems. It wasn't until we developed a problem that we had to find a better way to do things. My guess, by the way, about why Newton was shy in releasing his theory of fluxions is that he wanted the axiomatic framework. Let me try to argue for that. If you just look at the Principia, it starts with definitions, very, very clearly, laying out what the definitions are, what the laws are, the famous laws of motion. He's trying to do things just like Euclid's elements. Euclid starts with definitions. Euclid goes to the famous 5 postulates. So Newton, I claim, I guess, I hypothesize that Newton wanted to do calculus axiomatically, and it just 300 years later, instead of being called fluxions, is now called non-standard analysis. By the way, I'm going to be running an experiment this summer where I'm going to take a bunch of poor high school kids in New Jersey, and we're going to use Jeremy's axioms as the foundation. This was an experiment that my former PhD student, Andre Hernandez Espia, carried out and formalized the entire book 1 of the elements, where it really looks like the elements. It's not like Hilbert's axioms or Russell's axioms, where the objects don't directly correspond to a physical construction. So this is what day 1 is going to look like. We're going to try to figure out how to say what Euclid was trying to say, but do it formally. Postulate 1 is that for every pair of points, there's a line, so that both things are on the line. Postulate 3 is for a point and a center. Given a center and a point, there's a circle with a center through that point. All of this development, by the way, may eventually prove useful. If you remember, Thomas said that alpha proof is missing geometry. Geometry in the style of IMO. And so it's this kind of thing that may prove helpful there.
But will the tactics today have pictures?
Yeah, so there is, in fact, I forget what the student of yours is who... Wojtek.
Yeah.
Who and Andre implemented this.
Yeah.
So...
And you had a postdoc also.
Yeah.
How
So
do you take this kind of thing to school, to show school kids?
Yeah.
What's holding me back is that we can't. I want to prove that angular center is twice angular circumference, but I haven't got the picture.
So it is possible. It needs to be better.
It's possible, but someone has to do it.
Someone has to do it. Yeah. Well, LLMs are really good at coding. That job is much easier today than it was 6 months ago. But someone still has to do it. And it's been done to a degree, but I agree, it needs to be done to a much better degree so that it can fully be implemented. So this will be an experiment where we're not quite there yet. Here's another related question in this direction. How do you get more people to use Lean? If you want, how do we make people use Lean? And the answer is you don't. And the analogy I want to give is to tech. So if you think about what happened with tech, Knuth released it in 1978. At that time, every single mathematician is handwriting papers and giving it to a secretary to typeset. You wait a few weeks or a month, and you hope that what comes back, is somewhat resembling the document you handed to the secretary. Throughout the 80s, Spivak was really pushing for people to use AMS tech, but still very, very few people did. And then, beginning in the 90s, when LaTeX comes out, it's got a ton of macros. And by the year 2000, when this paper was written, very, very few mathematicians were still handwriting their own papers, among them my three collaborators and close friends, who still don't know how to tech. In fact, they've gone past the part where they don't need to know how to tech because they can handwrite their papers, scan it into an AI, the AI will tech it for them. Okay, so now nobody needs to know how to tech. And by the way, now my students, no one's downloading MicTech, installing pip install, anything. You just open Overleaf, it's right there, it's free, it's immediate, it's a web app, it doesn't matter if you're running a Mac or a PC. Okay, so this is what I call the Knuth constant. So this is the time to typeset, despite you needing $signs, backslashes, and curly brackets, relative to the time that you would handwrite. The second the Knuth constant went below 1, there was no AMS meeting where they said, now we mandate that everyone will learn tech. Right? People just did it. It's faster. It's more efficient. It's easier. So the same thing can happen with Lean. Everyone can switch to working formally voluntarily. So I realize this, the de Bruijn constant is the wrong metric. It's about lines of code divided by lines of natural language proof, but LLMs can just produce lines and lines and lines. That's not the measure. The measure should be time. The amount of time it takes to write a paper, not just formalize a paper, but discover mathematics while working formally, divided by the amount of time it would take to typeset a paper where if you are writing a 100-page analytic number theory paper with 30 parameters that are all moving around and you have to triple check every single lemma, and, because you don't trust yourself, and it's so easy to make a mistake, and this parameter needs to be less than that parameter to the 2/3, and everything's moving around. If you could do that formally, if I would love to be able to state one of my theorems in Lean. There's sort of the development of Lean, and then at some point it'll come, and I'll be able to actually do that, and that'll be beautiful. The instant that ratio, the ratio of the amount of time it takes to write a paper from the beginning formally in Lean to the amount of time it takes to write a paper now, the instant that ratio gets below 1, because of MathLib getting really good, automation getting really great tactics into MathLib, LLMs getting better, Lean being a free web app, whether it's GitHub Codespaces, Gitpod, liveleanlang.org, all of these things are, when they happen, everyone will just switch to working formally, voluntarily. We don't need a committee meeting about this. Okay, that's the proposal. In that direction, let me just show you one little prototype. So this is something that, again, I don't know how to code, I don't know how to use HTML, but I know how to ask an LLM, and I don't trust it. I take what it says and throw it into an actual website. And so this was just a baby little prototype of taking baby Rudin and throwing some baby Rudin problems and seeing what it could do. So here's the exercise. Prove that the convergence of a sequence implies the convergence of the absolute value. This is just a website. There's nothing you can do on it, except you can click this little button, Open Lean Editor. Of course, I'm not online, and so you can't see that there's a beautiful Lean Editor that pops up. And all right, I'm not going to try to fix it now. Trust me, it's really, really cool. There's all kinds of other things. Patrick Massot has this beautiful way that makes it look much more like mathematics. It still has exactly the same structure. You can click on anything, you can hover over everything. This is the Verso language. You hover over any object.
You should also say Kyle Miller. It's not only
Yes.
Massot, it's Massot and Miller.
Massot and Miller. Thank you. Thanks for that correction. So all kinds of experiments like this are going to be done in the near future, and people who, like me, are not programmers can just do it. So Kevin, you can code up that angle.
Your
thing.
website, and it is lovely.
Okay. Okay, you're on it. Yeah, I guess I did give the link. So yeah. So you just click and start playing, right? You have the freedom to express yourself however you want. You don't have to do anything. Nothing is forced. Okay, so there's still a lot of experimentation to be done in the teaching direction. Let's go to understanding and communication. So Tim says proofs are usually clear if they have a hierarchical structure. A main theorem follows from 3 lemmas that all have clear statements, and you can isolate them in different parts of the proofs. What he's invented is, okay, so this blueprint is not a good example. It's an engineering blueprint. We're trying to get somewhere. But for a communication blueprint, an educational blueprint, what you would have is a big bubble that has the main theorem, and then just 2 little bubbles out of it that are the main propositions. And if you zoom in, those bubbles turn into smaller bubbles. And inside those bubbles, you can go into the lemma and click on each lemma that you want to investigate individually, and so on. Okay? So there's all kinds of experiments that we could be running with, what the paper of the future looks like. It can be a PDF file, and the first line of the PDF file can be a link to a website where it's the same paper, but now you can play with everything. You can zoom in, you can ask an LLM, I don't understand this lemma, can you give me an example? We're headed towards a golden age, I think, of this kind of communication. And yeah, so I'll give Tim the last word. So computers will still do the boring bits for us, but they won't be quite as boring as they are now. However, this golden age, if it occurs, is unlikely to last for long. The next stage might be one where only a few outstanding mathematicians are still discovering proofs that are inaccessible to computers. Perhaps others would concentrate on teaching, but computers would probably be better at that than us anyway. In the end, the work of the mathematician would simply be to learn how to use theorem-proving machines effectively and to find interesting applications for them. This would be a valuable skill, but it would hardly be the pure mathematics that we know today. We'll see if that's what happens, but thank you for your time.
If you go back to your quasi-formalization, sorry, it might be a while back.
And
yeah. So you say it's the greatest short-term challenge. What do you think the main things to improve are? Do you think it's on the like LLM side, or do you think it's on the sort of tactics side? Because you were talking about having the tactics be shorter and stuff.
yeah, so it's every green arrow needs to get better, and then this part needs to get better. Everything needs to get better. So having conversations with LLMs is great, but they don't know what the hell they're saying. So once you zero in on an idea you're actually interested in, you say, can you make me a formal statement, formal natural language statement of that? If it looks right to you, you can suggest, and this is really at the level of lemmas. Like I don't expect it to be doing theorems, although if it can really do a great job at lemmas a lot, what's stopping it from bootstrapping lemmas into propositions and bootstrapping propositions into theorems? But first, let's get lemmas right. Well, I keep oscillating between we're very far from that and it's around the corner, or it's already here. In the sense that, as you saw in the example with Bateman-Horn, yeah, it got it wrong, but it really went through the informal statement and jumped straight to the formal statement, and with a little bit of, as long as you're allowed to interfere, I don't need it to be perfectly automated. As long as I'm allowed to interfere and it speeds up my workflow, that I'll use it. This is the part that right now is the real drain for me. When I'm working on the prime number theorem plus project, I'll write out formal statements. I have to scaffold things to a degree where this is exactly what somebody was saying, Flores was saying, I think, that you have to get it down to the level where just an engineer, a software engineer who knows some calculus can jump in and solve this sorry, right? They shouldn't need to know anything about prime numbers and anything about complex analysis. So this is the painful part where once I'm done stating the scaffold, I then have to go and write up a nice post for Zulip about what each of the tasks is and keep track of, okay, is this one really what I need? Who wants to claim this? It's very tedious, whereas if I just send it to Alpha Proof and it says, in 2 minutes, it says, here's 10 lines that close this, that's a much more just joyful way to work.
So I guess you did have a hammer there as well, in principle.
Yeah. I'm using the word alpha proof in place of the word sledgehammer.
Cool.
Yeah. I don't care what it is, right? I just want to do math.
You want all the bits to be better.
I want all the bits to be better.
I mean, one issue with this idea that is in all related ideas is those stories are also used for training. I mean, people come to Zulip, they are not yet lean experts, but they can do your stupid stories and then go up in skill. And so don't we fear that we lose this training?
That's a great question. Yeah, that's a great question. Well, there are other ways that they can get that training. But I agree, it's great training, and it's really good experience for them, and yeah, there is a loss.
Maybe we're telling them to do things that they'll no longer need to do.
That's another point.
So, sort of a related question. Thank you for that talk, which had a lot of provocative ideas. One of which is that it doesn't matter if the formal statements are wrong. And this sort of counter-argument that is most convincing to me is that, maybe that's true from the perspective of mathematics, to the point that, the community will eventually catch a mistake if it matters. But it's not so obviously true from the point of view of mathematicians, because it could have a practical, very negative effect on somebody's career if there's a mistake in their own work, and it's particularly tragic when it's a result of a mistake in somebody else's work that, say, their advisor didn't know about. I'm speaking from experience of, whereas the advisor, I feel very guilty that I didn't know that a sort of well-known, that some paper was dodgy when my student used in their work. What do you think about that?
That happens all the time now.
Sure.
Right? So I don't think we're gonna, it's not a panacea. It's not gonna solve all of our problems. All the same problems we have are gonna continue. It's just they might make us slightly faster, more agile, I want that department T. I want lots of ideas floating around, and LLMs let me have department T all day long without bothering my colleagues too much.
Right, but if more of the mathematics that's being generated is wrong than right relative to the current state, I feel like that's a negative trend.
So, absolutely, and that's why I said when Will Sawin said, you and Claude got this wrong, I said I got it wrong. The responsibility, if I'm using whatever tool I'm using to generate mathematics, and I'm putting out wrong mathematics, that's on me. I feel that that's a judgment, right? Everyone should decide for themselves how they feel about it. My personal opinion is if I put out mathematics and it's wrong, I'm not going to go blame anybody else.
Yeah, it was actually a question precisely on this. You used the analogy of self-driving cars. And
Maybe it's a bad analogy, but go on.
I think if self-driving cars crash, like when people are not paying enough attention because they're trusting the machine, I think it's like a lot of the responsibility is on the company selling these as a reliable tool that you can work with. And so certainly I understand the moral that you feel like you should be responsible yourself, but the next generation of mathematicians who are growing up on these, I don't know if they'll feel as responsible as you do. They'll have the same sort of underlying moral feeling.
So I did read the second part of it, which is, if the time comes when they tell me I can sit in the back seat and let it drive me, then it's no longer, when they tell me I'm no longer responsible, then I'm not responsible. Then it's their insurance, not mine. What's that?
We shouldn't get distracted about self-driving cars, but even now, okay, to sit in the driving seat, but you need to pay attention the whole time. I think people are inevitably going to be distracted by it.
Well, the thing stops, it yells at you.
Sorry?
It yells at you if you take your hands off of if you look away. It starts yelling. It's like actively watching your face to make sure you don't look away.
It'd be good if Lean would yell at you when you missed a constant.
Yeah, it would. It would.
I mean, it can also try to generate counter examples.
It does, and alpha proof, that's one of the great things about alpha proof. There was a line somewhere here as well, I think I missed it. Maybe it was at the very end. Anyway, it was. Tim also said it would be great when if it's very fast at stopping you from going down a wrong path by finding counter. Yeah.
I have actually a comment about this Kahneman's theory of two systems. There is a book by David Bessie that he suggests that mathematicians do not work in this Kahneman's two systems. There is a third intuition system.
Please.
Yeah, so the book is...
And what's the third intuition system?
Yeah, so, and he sort of illustrates that a lot of famous mathematicians do not use these two systems. They work differently. This is like intuitive mathematics. He very in detail describes Descartes, Grothendieck, and other super famous people, how they do that.
So, thank you for that comment.
Yeah.
I think back to chess, and there are players who play just, I feel like this is a good move, and there are players who sit there and calculate. And I think Magnus talks about the fact that he doesn't really calculate. He's calculated so much. Yeah. Like system 2 becomes system 1 with practice. So it's possible that mathematicians are somewhere between system 2 and system 1, where we've done the calculations so often, we have the intuition, we can sort of follow our noses even when we're doing complicated calculations.
Yeah.
Is that what
No.
No.
It's, yeah.
It's a completely
Actually,
different
it's
system.
A completely different system. And also, intuition of hundreds of mathematicians is not always right. Lots of people intuitively thought that the fifth axiom of Euclid could be proved from other axioms.
Yeah. Thanks.
Yeah.
Just got one final comment. I know we're out of time really, but it ends on maybe a slightly pessimistic note in that, you know, we're now in this amazing
Can't blame me for
golden
that.
age, or we're coming into this golden age that Tim described, but then that's going to be quite short, and after that, the whole thing is more or less admin. Is there anything we can do now to ensure that that doesn't happen, to prolong this golden age?
All I can say is I still think the same as I did then. So I still think the golden age will happen and will be short.
So enjoy it now.
Yeah, we're in it, I think.
But it's under our control still, right?
That's why it's the golden age.
We are designing the AI. Humans are still designing this AI, the AI. It doesn't have to be so short. We can design AI that is engages in a long-term collaboration with us, rather than takes over and just becomes so much better than us that we're obsolete.
Yeah, it's a great question. It's above my pay grade.
Yeah. Okay, anyway, wait, we should probably stop, shouldn't we?